A cosmic clock could run backward. Time could flow in reverse. That's the possibility a white hole presents. It's not fiction. It comes from the mathematics of Einstein's universe. The deepest laws of physics might allow time to reverse. A black hole has a theoretical twin in the equations. Its existence would shatter cause and effect. So which is more powerful, the mathematics that describes reality or the reality we see? Imagine a cosmic drain. That's what a black hole is. Its gravity is so strong that past a certain point, the event horizon, nothing escapes. Not even light. It's a one-way trip, but picture running that film backward. You'd see a cosmic fountain, a place where matter and energy erupt outward. Unstoppable, and from the outside, nothing can ever get in. That's a white hole. It's not a separate object. It's the mathematical mirror image, the dark twin reversed. A black hole has an event horizon you cross only inward. A white hole has one you cross only outward. Two sides of the same coin in Einstein's equations. The math for warping space and time is symmetrical. If a black hole is a valid solution, so is its time-reversed counterpart. Our universe shows us the drain everywhere. Stellar remnants, the supermassive beasts in galactic centers, but the fountain, the white hole, that's a ghost in the machinery. It exists only on paper. This possibility that physics might allow a region where time flows the opposite way, that link between white holes and reversed time isn't a side effect. It's the essence. To understand one is to question the very nature of the other. The math that makes this possible started with one set of equations. Albert Einstein published his general theory of relativity in 1915. It was a revolutionary idea. Gravity isn't a force, it's a curvature. The fabric of space and time itself curves. The core of the theory is 10 interwoven equations. The Einstein field equations, they're the rule book. They describe how matter and energy tell spacetime how to curve, and how that curved spacetime tells matter how to move. It was beautiful but notoriously difficult. Then, just a year later, a German physicist found a solution, Karl Schwarzschild. He was serving on the front lines during the First World War. He solved Einstein's equations for the simplest case, the empty space around a single, perfectly spherical mass, a non-rotating mass like an idealized star. His solution is the Schwarzschild metric. It's a precise mathematical description of how spacetime is warped by that object's gravity. At its heart is a term. It depends on the mass and the distance from the center. This formula revealed something. As you approach a certain critical distance, the Schwarzschild radius, the mathematics seems to break down. It produces a division by zero. That's the coordinate singularity, the mathematical location of what we now call the event horizon. But here's the crucial part. Schwarzschild's solution wasn't just a description of space outside a star. When mathematicians later fully extended this solution, people like Martin Kruskal, peeling back its layers, they found it described two complete and separate universes within its geometry. The equations contained a black hole region. All paths lead inward to a central singularity, but they also contained a white hole region, a point of origin from which everything is expelled. And these two regions were linked. They were connected by a narrow, tunnel-like structure through spacetime, what we now call an Einstein-Rosen bridge. A wormhole. The mathematics itself is timeless. It doesn't care which way the clock ticks. It presents a perfectly symmetric picture, a cosmic Rorschach test. The ink blot of gravity looks the same whether time runs forward or backward. This inherent symmetry in the equations is the seed. The entire idea of reversed time and white holes grows from it. Schwarzschild's solution had a hidden world inside it. The equations looked like they broke down at the event horizon, but that was just a trick of perspective. It was like using a map that gets distorted at the poles. The terrain was real, but the coordinates were wrong. To see the real landscape, you needed a better map. That map came decades later. Physicists Martin Kruskal and George Szekeres found it. They found a new coordinate system, a mathematical lens that wiped the distortion away. This was the Kruskal-Szekeres Extension. It didn't change the physics, it unfolded it. It took the limited view of Schwarzschild's solution and stretched it open. It revealed the maximal analytic extension of the spacetime, the full, unvarnished geometry hidden in Einstein's equations. What they revealed was astonishing. The complete picture wasn't just one universe with a black hole. It was a structure of 4 interconnected regions. Picture a vast hourglass-shaped diagram. The narrow waist in the middle is the wormhole, the Einstein-Rosen bridge. Flanking it are 2 separate, asymptotically flat universes, Universe 1 and Universe 2, forever linked by this fleeting tunnel. But the crucial parts are above and below. In the upper quadrant of the diagram lies the black hole. All paths once crossed lead inexorably down toward the central singularity. And in the lower quadrant, directly opposite, sits the white hole. This is the region in the past. All paths originate from its central point and flow outward, away. On a Kruskal diagram, the white hole isn't some distant object. It's a fundamental region of the spacetime, as inherent as the black hole itself. Geodesics, the paths particles follow, emerge from the white hole's singularity. They travel outward, crossing its event horizon into the external universe. They can never go back in. This extension is a mathematical mandate. The white hole isn't an optional extra. It isn't a quirky thought experiment. It is woven into the very fabric of this solution. To have the black hole described by these equations, you must also accept the existence of its time-reversed twin. The geometry is symmetric and complete. This pushes the question from pure mathematics into physical plausibility. If our best description of gravity insists this structure is possible, could it ever be real? Or is this a case where mathematics describes a beautiful phantom, a ghost in the machine of the cosmos that reality simply chooses to ignore? The diagram lays it all out. A silent challenge written in the language of spacetime itself. That symmetry in the equations is unsettling. It describes a universe where time is just another direction. But that's not what we see. We remember the past. A glass shatters and doesn't come back together. That direction, that's the arrow of time, and its main source isn't gravity. It's thermodynamics, the second law. It says entropy always increases in a closed system. Entropy is disorder, randomness. The universe moves from order to chaos. That's why heat goes from hot to cold, why a room gets messy. This increase, it's what makes time have an arrow. It makes yesterday different from tomorrow. And there's a conflict here. The basic laws of physics, Einstein's equations, quantum mechanics, they're symmetric in time. You could run them backward. But the second law isn't, it only points forward. So if the underlying rules don't care about direction, why do we see this one-way flow? The answer seems to be the starting point. Our universe began with incredibly low entropy, a highly ordered state at the Big Bang. Everything since has been the unraveling from that point, the mixing. The increase in disorder. Now black holes fit into this. They're not exceptions, they're the ultimate examples. Stephen Hawking showed that black holes have entropy. A huge amount of it. A black hole's entropy is tied to the area of its event horizon. It's the most efficient container of disorder there is. When matter falls in, the universe's total entropy goes up. Hawking radiation, the evaporation that also increases entropy. Black holes are thermodynamic engines. They drive time's arrow forward, and this is the wall a white hole hits. By definition, a white hole would be a source. It would eject matter and energy in an ordered, low-entropy state. From the outside, it would look like a violation of the second law. Order coming from chaos for free. like watching smoke form back into a perfect log. The math of general relativity might allow it, but the thermodynamics of our universe seems to forbid it. This isn't a small problem. It's a fundamental clash between geometry and disorder, between symmetric equations and our one-way reality. The white hole doesn't just challenge gravity. It challenges the reason we experience time at all. The second law of thermodynamics looks like a solid wall, but physics has a way with walls. The answer might not be bending the old rules. It might be finding new ones. There's a modern theory of quantum gravity. It offers a way out. It reimagines reality, and it gives white holes another chance. That framework is loop quantum gravity. Its idea is radical. It says spacetime isn't smooth, it's not continuous, it's woven from tiny loops, indivisible loops. A tapestry of finite threads, a granular structure at the smallest scale you can imagine, far smaller than an atom. This quantization of space and time has a consequence. It means there's a limit to squeezing, a smallest possible volume that challenges the classical picture, the picture of a black hole's heart. In Einstein's relativity, a collapsing star leads to a singularity. A point of infinite density where physics breaks down, but in loop quantum gravity that can't happen. The quantized fabric of space resists being crushed to zero. So when collapsing matter reaches that maximum density, something happens. A repulsive quantum force emerges. It's like compressing a spring to its limit. The inward collapse hits a barrier and it rebounds. That's the quantum bounce. In this picture, a collapsing star doesn't form an eternal black hole. It passes through a super-dense quantum phase, and on the other side of that phase, the matter expands again. What comes out isn't the star that fell in. It behaves like a white hole. Matter and energy are expelled. The event horizon's one-way nature is reversed. That transforms the whole concept. A white hole isn't a separate ghost from another universe anymore. It becomes the later stage of a black hole, the reborn, expanding phase of the same object. Think of it as cosmic metamorphosis. The caterpillar of a black hole forms a chrysalis. A chrysalis of extreme quantum gravity, and after an unimaginable duration it emerges. It emerges as the butterfly of a white hole. The timescales aren't human. For a typical stellar mass black hole, the bounce happens after many billions of years, far longer than the universe's current age, so the black holes we see are all still contracting. Their white hole future is in a distant, almost mythical epoch, but this idea offers something. It could resolve a puzzle, the black hole information paradox. Information about what falls into a black hole seems lost forever when the hole evaporates through Hawking radiation that violates a core quantum principle. But if the black hole transitions into a white hole, the information isn't lost. It's stored during the quantum phase, scrambled maybe, and then released back into the universe during the expansion. The white hole becomes the mechanism for cosmic memory, a guarantee that the story of what fell in isn't erased, just transformed, profoundly transformed. This speculative bridge between black hole gravity and quantum rules hints at a dynamic cosmos, a cyclical cosmos. It suggests a universe where even absolute endings might be gateways. Gateways to new beginnings. The mathematics of reversal finds a home, not in defiance of time's arrow, but in the deepest quantum structure, the structure of reality itself. The black hole information paradox. It's one of the deepest mysteries in physics, a conflict right at the heart of our understanding. On one side, you have quantum mechanics. It has this sacred rule, unitarity. Information is never destroyed. It can be scrambled, hidden, transformed, but never erased. The total quantum information of the universe is conserved. It's a perfect cosmic ledger. Every particle, every interaction is recorded. On the other side, you have general relativity and its black holes. When something falls past the event horizon, it's lost. Then Stephen Hawking showed black holes evaporate. They emit radiation, but that Hawking radiation is purely thermal, random noise. It carries no information about what fell in. So when the black hole finally vanishes, what happens to all that quantum information? In the classical picture, it's irretrievably lost. The ledger is burned. That's the paradox, two foundational pillars of physics making contradictory predictions. For decades, most physicists have bet on quantum mechanics being right. The information must escape somehow, but the how has been elusive. This is where the white hole, in its modern quantum bounce form, offers a possibility. It could be the cosmic reset button. In the loop quantum gravity scenario, the black hole doesn't evaporate into nothingness. It undergoes a quantum bounce. It transitions to a white hole phase. During that super-dense quantum phase, all the information of the infalling matter isn't destroyed. It's preserved, encoded in the quantum state of spacetime itself. Then, as the white hole expands and erupts, that information is released back into the universe, not as the original star or book or spacecraft, but in a radically transformed state. The quantum information is returned, the cosmic ledger is balanced, unitarity is restored. The white hole becomes the mechanism of cosmic memory. If this is true, the implications are staggering. A white hole wouldn't just be a localized reversal of time's flow somewhere in space. It would be an agent of quantum mechanical order on a universal scale. It would ensure the fundamental rules of reality remain intact, even in the face of gravity's most destructive phenomena. It turns a black hole from a cosmic shredder into a cosmic recycler. The ultimate paradox finds a potential resolution, not by discarding one theory, but by weaving them together through a new, deeper understanding of spacetime. This leads to a question: if white holes are real, and if they are the reborn remnants of ancient black holes, could we ever hope to see one? The search for observational signatures becomes the next great challenge. A hunt for the faintest echoes of a reversed cosmic clock. A universe that keeps its quantum ledger might still have other rules, fundamental rules that could stop certain structures from ever appearing. One of the most profound ideas is cosmic censorship. Roger Penrose proposed it. It's less a formal law and more a deep suspicion about nature. The conjecture is elegant. It says nature abhors a naked singularity. In a black hole, the singularity, that point of infinite density, is hidden. It's veiled by the event horizon. No outside observer can ever see it or be affected by its unpredictable, physics-breaking core. This censorship preserves causality. It keeps the sane, predictable universe separate from the chaotic unknown. Now consider a white hole. Its singularity exists in the past. It's the point everything erupts from. But is it hidden? A white hole's event horizon is a point of no entry, not no return. From the outside, could you see signals from that central singularity? If you could, that would be a naked singularity, a point where known physics breaks down, exposed to the cosmos. That would violate cosmic censorship. The universe, by this idea, might not allow such a thing to form or to persist. It would be too disruptive, too unpredictable. This leads to another possibility. The mathematics of general relativity, when stretched, allows for solutions with closed time-like curves, paths through spacetime that loop back on themselves. An object following such a path could, in theory, travel into its own past. It's the mathematical basis for a time machine. Some speculative white hole geometries, especially with rotation or wormholes, could create conditions where these closed curves form. A doorway to yesterday, but here we face another proposed veto. Stephen Hawking formulated the chronology protection conjecture. He argued the universe has a built-in mechanism to prevent time travel to the past. He suggested whenever conditions arise that could create a closed time-like curve, quantum effects would become overwhelming. Virtual particles would flood the region. creating an infinite surge of energy that would destroy the time machine before it could be used. The laws of physics, in this view, actively protect cause and effect. They protect history from paradox, so there are two powerful ideas acting as potential guardians. Cosmic censorship might forbid the exposed singularity of a white hole from ever being visible. And chronology protection might sabotage any white hole configuration that threatens to become a portal to the past. These aren't proven laws, they're profound conjectures from deep thinkers. They represent a belief that the universe, while mathematically rich, is also logically consistent. It may allow wild possibilities in the equations. But it also has layers of protection, layers that ensure stability, causality, a single, coherent flow of time for all observers. The white hole sits at a crossroads. It's a prediction of our most successful theory of gravity, yet it challenges the thermodynamic arrow of time, and it may be actively suppressed by these deeper principles. The question shifts. It's no longer just, can a white hole exist? It becomes, would the universe allow it to exist? The search for an answer moves from theory to the edges of the observable cosmos. To the faintest whispers in the data, gamma-ray bursts, they're the most violent explosions we can see, not just flashes. These are the biggest detonations since the Big Bang. In a few seconds, one burst can put out more energy than the sun will over 10 billion years. For decades, we've tied them to stellar deaths, a massive star collapsing into a black hole, or two neutron stars merging. That's the established story, and the evidence is strong. But what if a few of those bursts in all that data are telling something else? What if a short, incredibly intense gamma-ray burst isn't a birth cry, but a death rattle? A white hole's death rattle. It's a fringe idea, but it's there. A white hole in its final act wouldn't be a steady fountain. If it comes from a quantum bounce, it's temporary. After eons, it would finally exhaust its stored mass energy. And it would explode, a one-time, catastrophic eruption of everything it ever contained. From far away, that could look a lot like a short gamma-ray burst. A brilliant, focused beam of high-energy radiation coming from what looks like empty space. The profile could match immense energy from a point-like source, with no visible star or galaxy there before. No progenitor. That last part is key. Every known gamma-ray burst after the fact has been linked to something, a host galaxy, a remnant something. But what if we found one that truly came from nothing? A burst with no home, no prior stellar activity, no afterglow that fits a merger. That would be an anomaly. And it would beg for a wild explanation. A white hole's final firework display is one candidate. The challenges, though, are immense. Gamma-ray burst astronomy is precise now. We've linked long bursts to supernova in distant galaxies. We've detected gravitational waves from neutron star mergers that line up with short bursts. The evidence for the conventional explanations is robust. It's growing. A white hole event would be a solitary actor on a dark stage. It would leave no neutron star behind. No black hole, just an expanding cloud of radiation and particles. Trying to distinguish that from the messy aftermath of a normal explosion is, with current technology, nearly impossible. We're looking for a ghostly signature in a field already ruled by cosmic giants. Yet the speculation persists because it serves a purpose. It pushes observational science to ask sharper questions. To look deeper into the anomalies. Could that one strange burst, with unusual chemical signatures or a puzzling light curve, be something entirely new? The idea forces us to define what we're actually looking for. It asks us to paint a theoretical picture of a white hole death, so our telescopes might recognize it if it ever happens. This search goes beyond gamma rays. If a white hole is expelling matter, it might also be a source of those mysterious, ultra-high-energy cosmic rays. Or it might produce a unique neutrino signature. We're compiling a wanted poster for an entity that may not exist. but the hunt itself expands our understanding of what can exist. It turns the philosophical mystery of reverse time into a concrete checklist for astronomers, and if every item on that checklist stays unchecked, that's an answer too. It tells us that if white holes are real, they're either impossibly rare, or they wear a perfect disguise, looking exactly like the stellar catastrophes we already know. There's another place a white hole might be hiding, an older one, not in the future of some dying star, but back at the very beginning. The idea is that white holes could be primordial. Relics from the universe's violent birth. Right after the Big Bang, everything was incredibly dense and hot. Spacetime was churning, a quantum foam. In that chaos, tiny density fluctuations got stretched to extremes. Some spots slightly denser could have collapsed under their own gravity. That's the idea of primordial black holes. But if the math is symmetric, the opposite could have happened too. A region with slightly lower density in that early foam might have behaved differently. Instead of collapsing inward, the immense pressure of the infant universe could have pushed it outward. It might have undergone a quantum bounce right at the start, and what comes out of that, a fountain, energy and matter erupting into the young cosmos. A white hole, not from a star's death but from the universe's birth pangs. These primordial white holes would have been fleeting. They'd erupt their entire contents in an instant. Just a burst of particles and radiation into the space around them. Then they'd be gone, so it completely detaches the idea from any stellar life cycle. They become one-off events, singular eruptions written into the early universe. Their existence would be a direct signature of the quantum gravity era. A fossil from before the first stars, before atoms, when all forces were one. That also makes them very hard to rule out. How do you look for something that flashed and vanished in the first fraction of a second? You look for echoes. That sudden energy injection from a primordial white hole eruption could have left imprints on the oldest light we see, the cosmic microwave background. A slight unevenness, maybe a tiny hotspot, or a specific pattern in the polarization of that ancient radiation, or the matter it expelled could have influenced the formation of the very first structures. An anomalous cluster of ancient stars, or a void that shouldn't be there according to our models. The primordial white hole idea is an end run around many thermodynamic objections. In the frenzy of the Big Bang, the normal rules of entropy were still being written. A local reversal, a fountain of order might not have been the paradox it would be today. It could have been part of the universe's initial sorting process. So this transforms the white hole from a potential destroyer of causality into a potential builder of the cosmos. A creative force. If they existed, these primordial fountains could have seeded galaxies or created certain vast, empty regions of space. They become probes, not of stellar graves, but of creation itself. They offer a window, however smudged, into the moment time began, and that leads to the ultimate, almost philosophical question their possibility forces us to confront. The deepest thing here might not be time, it's space, a bigger space. If our universe is just one bubble in a kind of foam, then Einstein's equations, their symmetries, they suggest something else. A white hole might not be something inside our universe. It could be a way out that connects to models like the inflationary multiverse, where our universe is one bubble among countless others, each with different laws budding off from this inflating background. The math that gives us wormholes, Einstein-Rosen bridges, could link these separate worlds, so a black hole here that drain might not end in a singularity. Its tunnel could go through the higher dimensional bulk of the multiverse and open somewhere else, and to whatever is in that other bubble, that opening would look like a white hole. A sudden fountain of matter and energy erupting into their cosmos from nowhere. In this view, the white hole isn't about reversing time in one universe. It becomes a connector, a one-way gateway between islands. What falls into a black hole here becomes the stuff for a new galaxy over there. That changes it from a paradox into a mechanism. For seeding, it suggests a universe that isn't isolated but porous, where information and energy might flow between realms through the gravitational plumbing of wormholes. That has wild implications for causality, for time's arrow. Each bubble universe likely has its own beginning, its own Big Bang, its own thermodynamic starting point. If a white hole is the mouth of a tunnel from another universe, then from the receiving universe's perspective, it isn't reversing time, it's an origin point. A secondary creation, the matter it ejects has its own history, its own entropy story from where it came from. That entropy then mixes with the new universe's own flow. It adds complexity but doesn't reverse it. The arrow of time in each bubble stays intact, pointing forward from its own beginning. The white hole is just a delivery service. Bringing packages from one timeline to another, that's a completely different perspective on their role. They're not time machines, they're teleporters. Not destroyers of causality, but couriers across the vast architecture of reality. They become potential evidence for a multiverse, not through direct observation, but through their effects. If we ever found strong evidence for a white hole, it could be the first clue that our universe isn't alone, that we're part of a far grander, interconnected structure, where every ending in one place might be a beginning somewhere else. The idea of a white hole as a delivery service leads to a deeper question. What if it delivered everything? What if the package was our whole universe? That's white hole cosmology. It moves from a strange object to a theory of everything. It says our Big Bang wasn't an absolute beginning. It was an event, a white hole eruption on a cosmic scale. In this view, the initial singularity wasn't the start of time. It was the mouth of a wormhole. A bridge from a parent cosmos. Our entire observable universe, all of it, would be the expanding aftermath, matter and energy erupting from that white hole. This changes the frame. The hot, dense state we call the Big Bang becomes the interior of the white hole just after it formed. The rapid expansion, inflation, is the explosive outflow. The cosmic microwave background is the cooled remnant of that fireball surface. It offers an alternative to the standard inflationary model. Here, inflation isn't a mysterious field-driven process in a void. It's the natural geometric consequence, matter and energy pouring into a new region of spacetime from a higher density source. The uniformity of the cosmos, the flat geometry, the horizon problem, these might be explained not by a brief super-fast expansion, but by the pre-existing conditions of the matter that erupted. That matter came from a parent universe that had already reached high entropy, high equilibrium. When it burst through, it was already smooth. This is a deeply controversial idea. It has no direct empirical evidence. It's a framework, a narrative written in the language of general relativity's most exotic solutions, but its power isn't in proof. It's in perspective. It forces a shift in how we view origins. The Big Bang is no longer the ultimate beginning. It becomes a transition, a phase change in a much larger, possibly eternal, multiverse. Was our beginning unique or part of a cycle? White hole cosmology suggests a cycle. A black hole forms in a parent universe, maybe from a collapsing star or an entire region. Its interior, in some quantum gravity theories, doesn't end in a point. It becomes the seed for a new spacetime. That newborn region then expands as a white hole into its own domain. Our universe, in this vision, every black hole could be a Big Bang for a new reality, and our own cosmos might be the white hole offspring of another. This sidesteps the troubling question of what came before the Big Bang. There was no before for our time, but there was a cause in a broader meta-time. The white hole becomes a mechanism of cosmic reproduction. It challenges the story of a single, isolated creation event. It paints a picture of a fecund multiverse, where universes beget universes through the gravitational extremes of black and white holes. While untestable now, this idea stretches the imagination. It asks us to see our cosmic history not as the main story, but as a single chapter in an epic far beyond our view. The search for our origin might be the search for our parent. This symmetry goes all the way down to the fundamental laws. Physics has this perfect balance, a set of invariances. They define what can happen, what can't. Three of the most profound ones are called C, P, and T: charge conjugation, parity, time reversal. Charge conjugation flips a particle to its antiparticle. Parity is like a mirror. It reverses left and right in space, and time reversal flips the direction of time. Individually, these symmetries can break. We see that in experiments, but there's a powerful theorem, the CPT theorem. It says the combined operation of all three swapping particles for antiparticles, mirroring space, reversing time, that's a perfect symmetry. Unbreakable. Any theory that follows special relativity and quantum mechanics has to obey CPT invariance. It's a cornerstone. Now take a black hole. A black hole is a process. Matter and energy fall in, moving forward in time. It has a charge, a spin, a specific configuration. What's the CPT reverse of that whole system? You'd flip its charge to the opposite. You'd mirror its rotation, and you'd reverse the flow of time. What you get is an object with opposite charge, mirrored spin, all its processes running backward. Instead of matter falling in, you see matter erupting out. Instead of an event horizon you can only cross inward, you see one you can only cross outward. That's the precise description of a white hole, not just a geometric twin, a CPT mirrored twin. This gives an argument of staggering depth for white holes. They're not optional. If our universe is described by a theory that unites quantum mechanics and gravity, a Lorentz invariant quantum gravity theory, then that theory has to respect CPT symmetry. And if that theory contains black holes as valid solutions, then by the iron logic of CPT, it must also contain their perfect symmetric partners, white holes. They become a mathematical necessity, a requirement for the universe's fundamental balance sheet that shifts the perspective entirely. The question is no longer, could white holes exist? The deeper question becomes, if our theories are correct, how could they not exist? Their absence would be a paradox. It would mean our most cherished symmetry principles, principles confirmed in countless collider experiments, break down at the scale of gravity's ultimate triumph. The white hole becomes a test, a probe of whether the quantum world and the gravitational world can truly be united under one consistent set of rules. It suggests that for every process in the cosmos, a time-reversed counterpart must, in principle, be inscribed in the laws. The universe's deepest architecture may be built not just on matter and force, but on a profound and perfect mirror. The laws have this symmetry, but in practice it creates a puzzle. How would a white hole ever form? We know how black holes happen. A star runs out of fuel, its core collapses under its own weight. Gravity wins. It's a process we can see. For a white hole, it's the reverse. You'd need a singularity, a point of infinite density to just appear, and then start throwing everything outward. There's no classical process for that, no law of gravity acting on normal matter that would cause it. It's like a fountain starting from nothing, no source, no pump. That's the formation problem. It's why many physicists say white holes aren't physical. The math is beautiful, but there's no door to reality. The proposals we have are attempts to build that door. The quantum bounce idea says a white hole doesn't form on its own. It's a later phase of a black hole's life after a quantum change. The primordial idea says they weren't made by stars. They were imprinted in the early universe. Both are compelling, but both rely on physics we haven't confirmed yet. They're stories of origin, not observed mechanisms. In the clean, classical world of Einstein's equations alone, there's no dynamical path to create one. You could write one into the starting conditions of a universe as a given. But you can't show how it would arise naturally from cosmic events. It's a mathematical endpoint with no clear beginning. This paradox forces a choice. Either we accept that our best theory of gravity predicts objects that can't be born, which seems like a flaw, or we look for a reinterpretation. Maybe white holes aren't objects to be found. Maybe they're clues about the limits of our theories, or about a deeper layer of reality where our ideas of beginning and end are too simple. Their stubborn presence in the math, despite being practically impossible, is a persistent whisper. It suggests we're missing a critical piece of the puzzle, a piece that would explain not just how things end, but how new things can truly begin. That perfect symmetry in the math is a clue. Maybe we've been asking the wrong question. We've been looking for white holes like they're separate objects, something to discover out there, like a new planet. But the equations point somewhere else. They might not be objects at all. They're just a region, a necessary part of the full picture of a black hole's spacetime. The maximal analytic extension, it's not just a fancy diagram. It's the full story the geometry is telling. In that view, the white hole region is the past. Not necessarily our universe's past, but the past of the black hole itself. It's the mathematical description of all the paths matter could have taken to eventually fall in. Those paths traced backward in time, they converge. They converge on the white hole's singularity, so the white hole isn't some fountain erupting now. It's a record, a geometric record of everything that ever could have formed that black hole. Could be matter from another universe coming through a wormhole. Or matter from some distant, disconnected part of our own cosmos, pulled in by gravity over eons. The white hole is that point of origin, written into the fabric of the solution. This perspective is humbling. It downplays the idea of a white hole as a physical thing erupting in our present. Instead, it elevates it as a structural feature. A fundamental part of understanding the complete, four-dimensional shape of spacetime around a gravitational monster. The black hole and the white hole aren't two things. They're two aspects of one thing, the full, unvarnished geometry of a massive, non-rotating point in Einstein's universe. This interpretation keeps their mathematical necessity without needing some bizarre birth process. They're always there in the math as part of the package. You can't have the black hole solution without its extended regions, which include the white hole. To remove it would be to cut the story short, to ignore the full symmetry the universe's rulebook allows, so maybe white holes aren't waiting to be found. They're already found every time we write down the Schwarzschild metric and extend it fully. They exist as possibilities, as a testament to the profound, sometimes disorienting completeness of general relativity. They remind us that what we observe, the black hole drain, might be just one chapter in a much longer, more interconnected cosmic biography. The search shifts then. Not to finding an object, but to understanding whether this breathtaking mathematical completeness reflects a physical reality, or if it's just a beautiful map to a territory nature chooses not to inhabit. Even the biggest mysteries in the universe might be connected. They don't just exist separately, they seem to speak to each other. We've mapped the stars, but most of the mass is something else, dark matter. We see the universe expanding, but something is pushing it faster, dark energy. These are the main things shaping everything, and we don't know what they are. So when you hear about a white hole, a theoretical thing, you start to wonder, could it have something to do with those dark components? This is just speculation. A thought experiment, but it shows how we want to pull the clues together into one story. Take dark matter. We know it's there because of gravity. It holds galaxies together in these huge, invisible halos. But we've never seen a particle of it. Now imagine a white hole in the early universe, a brief, explosive event. What if it didn't just release normal particles? What if, in that fireball, it made something stable, something that doesn't interact with light, an exotic matter that just stays? that sudden injection could have created the first clumps of dark matter. Those clumps would then pull in normal matter. They'd become the anchors for the first galaxies. In this picture, white holes aren't just curiosities. They could be factories, each one a seed for a galaxy's dark heart. Then there's dark energy, even stranger. It's making the expansion speed up. It acts like a negative pressure in the vacuum of space itself. Some theories say it's a geometric effect, a property of spacetime on the largest scales. And that's where a white hole's interior gets interesting. Mathematically, the inside of a white hole is its own little expanding universe. Could the geometry there, or the repulsive forces that might power it, have a larger counterpart? Could the fabric of spacetime itself have properties that, averaged across the whole cosmos, show up as that gentle push we call dark energy? It's a long shot, connecting a quantum bounce to the fate of everything. There's no established theory here. It's more of a thematic echo. Both ideas deal with expansion. With anti-gravity, with the latent energy of space, noticing these connections matters, not because they're likely true, but because they show how we think when we don't know. We have three huge mysteries: white holes, dark matter, dark energy. Each is a gap. The instinct is to try and bridge them, to see if one unknown can explain another. It's a kind of narrative triangulation. We could be completely wrong. Dark matter is probably a new particle. Dark energy is probably a property of the quantum vacuum. White holes might be mathematical phantoms, but by asking if they're related, we push our models. We test the limits of imagination. This whole exercise points to something deeper about cosmology. We're not just listing objects in the sky. We're trying to read a single, interconnected story, written in gravity and geometry and quantum possibility. Every strange idea, even the fringe ones, is a probe sent into the dark, not just the dark of space, the dark of our own understanding, hoping to hit something solid. To finally make sense of the shadow universe we live in, the equations give us a picture, but it's a still frame, a snapshot. Reality isn't still, it's moving. It's messy. To see if these mathematical ideas could survive in a real cosmos, we have to make them move. We have to simulate them. That's where supercomputers come in. The field is called numerical relativity. It's a way to take Einstein's equations and make them dance. You break down spacetime into a grid, a vast, evolving grid. A digital universe of billions of points. You program the starting conditions, the mass, the spin, the shape of space. Then you let the physics play out. Millisecond by millisecond, this is how we've watched black holes spiral together and merge. We've seen the gravitational waves ripple out. These simulations are stress tests. They ask, if we build this thing by the rules, does it hold together? So what happens when we try to build a white hole? Direct simulations are rare. There's a reason. A classical white hole as a starting point is what physicists call a causal. It begins with the answer, the eruption, without a cause in its own past. It's like programming a movie to start with an explosion and asking the computer to figure out what came before. The simulation often doesn't know what to do. The result is almost always violent instability, that balance, the outward pressure against the pull of gravity. It's too perfect. The slightest perturbation tips the scales. A bit of matter, a gravitational wave from a passing star. In many runs, the white hole horizon doesn't hold. It collapses. It becomes the very thing it was meant to oppose. It becomes a black hole. These digital experiments suggest that even if a white hole could form, it might be a fleeting moment, a cosmic hiccup, immediately swallowed by gravity. But the computational lens is also looking at more nuanced ideas. Some researchers don't simulate a white hole from nothing. They model the quantum bounce. They start with a collapsing star, a black hole. Then they introduce the repulsive effects of quantum gravity at the highest densities. they watch to see if a stable rebound happens. And what the aftermath looks like. Does it spew matter out in a chaotic burst, or in a more structured way? Other studies probe wormholes, those theoretical tunnels connecting black holes to white holes. Could such a structure be held open, even for an instant, held open by exotic matter or quantum effects? Or does it pinch off immediately? These supercomputer universes are our laboratories for the impossible. They give a dynamic context to static equations. When a simulated white hole configuration crumbles in a fraction of a second, that's a powerful argument. It suggests nature might have a preference, a bias toward the one-way street of the black hole. The simulations don't prove white holes can't exist, but they show how fragile they would be. How militantly unstable in the rough and tumble of the real cosmos. This computational work changes the question. It moves from a philosophical "could it be" to a practical "could it last?" And so far, the digital cosmos seems to be whispering a reply, a consistent if tentative reply. The equations are clean, reality is lived, a white hole reversing time's flow. That's not just a cosmic curiosity. It's a philosophical earthquake. The first casualty would be causality. Cause always comes before effect. That's the bedrock. In a world with time reversal, an event could be its own cause. An effect could loop back and create its own origin. The universe's story wouldn't be a straight line anymore. It could become a tangled knot, no clear beginning, no clear end. And this isn't abstract. It strikes at how we understand everything. A dropped glass shattering, the choices that shape a life. Our entire legal and ethical framework is built on a chain of cause and effect. Responsibility depends on it. If that chain can be broken or reversed, then guilt, intention, consequence, they start to unravel. Imagine a crime where the punishment could theoretically occur before the act. The logic of justice collapses, and that leads directly to the grandfather paradox. If you could travel to the past, could you prevent your own birth? The paradox isn't a plot hole, it's a profound logical warning. It suggests consistent time travel to the past might be impossible, not just physically. Logically, a universe that allows such paradoxes might be a universe that cannot sustain coherent thought or history. Philosophers have wrestled with the nature of time to make sense of this. Is time a series of moments, one flowing into the next? That's the a series view. Past, present, future are real and changing. Or is time more like a block? A four-dimensional universe where all moments exist equally, past, present, future, all just there. Our consciousness just moves along a fixed track. That's the B-series, eternalism. In the block universe, your birth, your life, your passing, they all exist eternally. In that view, time travel wouldn't create new history. You would always have been part of the fixed past you visit. Your actions were always part of the story. That sidesteps the grandfather paradox, but it introduces a chilling determinism. If all moments are equally real, then choice might be an illusion. Our sense of free will, of shaping the future, becomes a passenger's view, a landscape that is already and always there. White holes as portals to reverse time force us to choose between these frameworks. Does physics allow the a-series, flowing time, to be genuinely reversed? Inviting paradox, or does it support the eternal block, where reversal is just a journey to another part of the fixed structure? Our lived experience screams for the first. We feel time passing, we make plans, we feel regret, we hope. This linear, irreversible timeline isn't just a perception, it's the stage for human meaning. For ethics, for love and loss, the very possibility of white holes, then, is more than a physics puzzle. It's a mirror held up to our deepest selves. It asks what is more fundamental, the mathematical symmetries written into the cosmos, or the arrow of time written into our consciousness. The search for these cosmic fountains becomes a search for whether our story is truly ours to write, or if we are reading from a script that was completed at the dawn of time. Physics classrooms are where wild ideas have to prove themselves. A white hole, even as a speculation, teaches something essential. It makes you look past the simple diagrams to see the geometry that's actually in the equations. When you teach general relativity, you start with the Schwarzschild solution, the space warped by a mass. But that's just the start. The real teaching is in the maximal extension, the Kruskal diagram. That's where you first see the symmetry of the full spacetime. The black hole is there, but also its mirror in the past, the white hole, and the wormhole that connects to other universes. This isn't optional, it's necessary. It shows that a solution to Einstein's equations isn't just about a star. It's a whole universe of possibilities. By following the paths, the geodesics, through all four regions, you see how geometry decides what happens. How one choice of coordinates can hide a cosmos, and a better choice reveals it. The white hole becomes a fixed point on that map, a place that's mathematically required, even if it's physically unlikely. That confrontation matters. You have to ask, why don't we see these? And that question goes straight to modern physics. It shows the gap between a mathematical possibility and physical reality. The instability in simulations, the problem with the second law of thermodynamics, these aren't flaws. They're successes. They show where classical general relativity by itself hits a wall. Where it points to something more. By struggling with the white hole's unphysical nature, you understand boundary conditions better, the universe's initial state. Cosmic censorship, the deep link between entropy, disorder, and the direction of time. It makes the need for a quantum theory of gravity feel concrete. Not abstract. To fix the white hole paradox, you have to combine Einstein's geometry with the rules of the quantum world. So the white hole is more than a maybe. It's a perfect thought experiment, a sandbox. It asks you to hold two contradictory ideas, to accept the solution's mathematical perfection while doubting its physical truth. That tension is where understanding deepens. It trains physicists not just to calculate but to question, to look at elegant equations and ask, what story is this geometry telling? And is it a story our universe can actually tell? Science fiction has always reflected our fears about the universe. The idea of reverse time, of cosmic doorways, that was in stories long before the term white hole existed. So when these mathematical ideas did appear, they were already set up for drama. There's an episode of Star Trek Deep Space Nine called The Visitor. It uses something called a subspace inversion, which is really just a white hole by another name, and it acts as a kind of tragic anchor in time. It traps a character outside of normal time. And the story becomes about loss and devotion between a father and his son over decades. In that story, the white hole isn't a source of matter. It's more like a prison made of moments. A plot device that warps cause and effect for emotional weight. It turns a physics speculation into a way to talk about love and memory and sacrifice. In books, the approach can be more direct. A physicist named John G. Kramer wrote a novel called The White Hole. In it, the phenomenon is a gateway, a door to another universe. These different stories have something in common. They take the white hole from a sterile mathematical concept and make it a narrative tool, a source of limitless energy. A doorway to other realities, a time machine you could control. The fiction focuses on utility and on consequence. It asks not how it works, but what we would do with it. That creative freedom is both useful and a distortion, because the actual math is far less cooperative. A classical white hole isn't a stable gateway you could fly through. It's probably violently unstable. It would collapse at the slightest touch. It doesn't offer free energy. It would be a brief, catastrophic eruption, still obeying conservation laws. And its link to reverse time, while profound in theory, is tangled up in quantum gravity and thermodynamic impossibilities. Fiction sands down those rough edges to serve the story. But this cultural lens is still valuable. It shows how esoteric scientific ideas filter into public awareness. The name itself, white hole, is a gift from popular culture. It's the perfect counterpoint to black hole, and it immediately suggests its imagined function. These stories, for all their inaccuracies, do something important. They take the chill out of the equations. They make the unimaginable feel close. They fuel public fascination with theoretical physics by connecting it to human themes. The desire to undo mistakes, the longing to explore, the dream of transcending our limits. This process of cultural translation always distorts, but it also plants a seed of interest. Someone captivated by a Star Trek episode might later look for a documentary or a science book. They start a journey from narrative wonder toward scientific curiosity. So the white hole exists in two parallel universes. One is the precise, austere world of differential geometry and quantum field theory. The other is the vibrant, metaphorical landscape of human stories. One asks if it can be, the other asks what it would mean. Both are part of how we relate to the cosmos. They remind us that our quest to understand the universe is never purely clinical. It's always and forever a human story. The mainstream view in physics is deeply skeptical. White holes are seen as beautiful phantoms, intriguing solutions in the equations, but almost certainly not real objects. This skepticism isn't dismissive. It's rooted in the foundations of how we understand reality. Stephen Hawking explored their implications but considered them unlikely. Other physicists call them mathematical artifacts, elegant curiosities that appear when you stretch a theory to its limits, beyond where it applies to the physical world. General relativity is a classical theory. It doesn't account for quantum effects. It doesn't dictate what must exist. It only describes what's possible within its own framework. And the leap from mathematical possibility to physical reality is vast. There are several concrete criticisms. First is the thermodynamic violation. A white hole ejecting ordered matter seems to contradict the second law of thermodynamics. The relentless increase of disorder. Speculative mechanisms like quantum bounces try to address this, but they're unproven. Second is the formation problem. We have a clear pathway for black holes. A massive star collapses, but there's no known classical process to create a white hole's past singularity from nothing. How would it even begin? Third is instability. Numerical simulations suggest that even if one could form, it would be exquisitely fragile. The slightest perturbation, a single particle of dust, could destabilize it and cause it to collapse into a black hole. They'd be cosmic mayflies, vanishing in an instant. Most damning is the complete absence of evidence. After decades of sophisticated astronomy, from gamma-ray telescopes to gravitational wave detectors, we've seen nothing that requires a white hole for explanation. Every extreme phenomenon has a compelling explanation within standard astrophysics. The burden of proof rests with the extraordinary claim, and for white holes, the evidence isn't just thin. It's entirely absent. This critical perspective is the essential counterweight. It's the rigor of the scientific method. Extraordinary claims require extraordinary evidence. The universe is under no obligation to satisfy our desire for symmetry or narrative elegance. Our task is to follow the evidence, not our favorite equations. So the story of white holes lies in a fascinating limbo, a permanent question mark, waiting for a future observation or theory to either finally bring it to life or to gently close the book. The absence of evidence isn't evidence of absence. It's a challenge. It means you have to look deeper. You need better tools. You need sharper questions. The search for a white hole has always been a search for a ghost, but a ghost can leave a footprint, not a glowing fountain you see in a telescope, a tremor. A tremor in the fabric of spacetime itself. So the future of this hunt is about listening to the universe in entirely new ways, LIGO and Virgo, our first gravitational wave detectors, they opened a new sense. They heard collisions, black holes, neutron stars, but they listened to a specific range, a high-pitched cosmic chirp. The next generation wants to hear the bass notes. The low, rumbling frequencies, frequencies that could carry signatures of events that are too vast or too subtle for our current ears. That future is LISA. The Laser Interferometer Space Antenna, a constellation of 3 spacecraft. They'll fly in a giant triangle millions of miles across, orbiting the Sun. It will detect gravitational waves with wavelengths so long they pass right through Earth. They go unnoticed, so what could it hear? Maybe the final moments of a supermassive black hole merger. One from the early universe, or the gentle hum from cosmic strings, the strings from the Big Bang, and maybe, just maybe, the unique gravitational fingerprint of a quantum bounce. That moment a collapsing black hole reaches maximum density and it rebounds, that transition from implosion to explosion would send a very specific ripple through spacetime. A signal unlike any collision, a birth cry in reverse, so LISA wouldn't see a white hole. It might hear its formation, or really its transformation. From one state of being to another, and then beyond gravitational waves, there's the oldest light, the cosmic microwave background. It's a fossil, a snapshot of the universe when it was just 380,000 years old. Its subtle patterns, those tiny temperature variations, they tell the story of what came before. So could a primordial white hole, erupting in that first second, have left a scar? A distinct circular hotspot, or a specific twist in the polarization of that ancient light, like a stone dropped in a pond, leaving ripples that freeze into the sky. Researchers have modeled these possibilities. The signatures would be faint, they'd be buried in noise, but our maps of this afterglow are becoming exquisitely detailed. From observatories like the Simons Observatory, from future space missions, we will sift that noise with finer and finer combs. We'll be looking for the impossible fingerprint in the most fundamental data we have. The search is also driven from theory. The ideas of loop, quantum gravity, string theory, they're not yet complete, but as they mature, they have to make contact with reality. They have to move from beautiful mathematics to testable predictions. So the next phase for LQG could be to precisely calculate the duration of the quantum bounce phase, or the spectrum of particles and radiation a white hole would emit upon its final explosion. String theory, with its extra dimensions and brains, it might predict how a white hole in a higher dimensional bulk would appear to us. To us in our 4-dimensional slice, these predictions give astronomers a shopping list, a specific set of signals to cross-check, to check against the strange events their telescopes record. Without that guidance, we're just guessing, and this quest, for all its long odds, it serves a purpose, a profound purpose. It's a catalyst, the dream of finding a white hole or proving its impossibility. It pushes engineering to its limits. It demands more sensitive detectors, more powerful telescopes, faster supercomputers. It forces theorists to sharpen their models, to confront the messy thermodynamics of the real world. To bridge the chasm between quantum mechanics and gravity, the white hole is a North Star on the map of ignorance. We may never reach it. But by aiming for it, we navigate into uncharted territories of physics and technology, and we discover other wonders along the way. The search itself keeps the possibility alive, not as a likely reality, but as an engine, a powerful engine for exploration at the furthest frontiers of human understanding. That search for a footprint, it goes beyond physics. It's a kind of meeting point, a place where 3 major currents of human thought come together. The white hole isn't just an astrophysical idea. It's a story written in the language of mathematics, interpreted by physics, questioned by philosophy. To really get it, you have to listen to all 3. Pure mathematics gives the first voice, the most elegant one. It speaks in the clean, absolute language of differential geometry, which is the study of shapes and spaces, but not the simple shapes we see. It deals with intrinsic curvature, with manifolds, the multidimensional landscapes where our universe exists, the Schwarzschild solution, the Kruskal extension. These aren't just physics formulas. They're rigorous geometric theorems. They describe a complete, self-consistent structure. The white hole emerges from that, not from a guess about nature, but from the logical necessity of completing a geometric picture. Mathematics asks what's the full shape implied by these rules, and it answers with a symmetric map, a breathtaking one that includes regions we never expected. It provides the pristine framework, free from the messiness of reality. Then theoretical physics steps in. It takes that beautiful mathematical structure and asks the brutal, practical question. Does our universe actually use this blueprint? Physics applies the stress tests, thermodynamics, quantum mechanics, observational evidence. It wrestles with entropy and instability. It looks for fingerprints in gravitational waves, in ancient light. Physics is the translator between the abstract world of perfect shapes and the tangible, noisy, one-way universe we actually live in. It's where the mathematical possibility meets the physical maybe, and standing beside them both is philosophy. Its role is interrogation. It looks at the map drawn by mathematics and the evidence gathered by physics and asks, what does this mean for reality itself? If the equations suggest time can be reversed but our experience says it cannot, which is more fundamental? Is time a real, flowing river or a fixed dimension in a block universe? What does the potential for a white hole tell us about causality, about free will, about the nature of existence? Philosophy forces us to confront the implications. It reminds us that science doesn't just collect facts, it seeks understanding. This synergy is where the profound breakthroughs happen. Einstein's leap from the mathematics of curved geometry to a new theory of gravity. The quantum revolution, born from wrestling with the philosophical implications of light and atoms. These weren't isolated triumphs in one field, they were conversations across disciplines. The white hole sits in this interdisciplinary space. To dismiss it as just a mathematical artifact is to ignore the geometric truth it reveals. To accept it as a physical certainty is to ignore the thermodynamic laws that govern our reality. And to not wonder about its philosophical meaning is to miss the point entirely. Appreciating this convergence changes how we see the cosmos. Understanding the universe requires more than solving equations. It requires the mathematician's love of elegant form, the physicist's insistence on empirical proof, and the philosopher's relentless questioning of what it all means. This holistic view doesn't provide easy answers about white holes. Instead, it frames the search itself as a grand human endeavor, one that prepares us to weave these separate threads into a final tapestry of thought. That convergence of disciplines gives us the full picture. We started with a simple fact, a fact written in geometry. Einstein's equations for gravity are symmetric. They describe a universe where time can run backward as easily as forward. From that mathematical seed, we followed the path it grows into. We saw the white hole emerge. Not as a whimsical idea, but as the logical, time-reversed twin of a black hole within the maximal extension of spacetime. The mathematical possibility is robust. It's not a mistake, it's a feature of the theory's internal consistency. Yet as we traced this elegant possibility outward, we met resistance. The real universe isn't a vacuum of pure geometry. It's filled with process, with disorder, with an irreversible arrow. Thermodynamics presented the first barrier, the greatest barrier. The second law insists on increasing entropy. On the one-way flow from order to chaos, a white hole ejecting ordered matter seems to defy that rule. Then came the questions of formation, of stability. How could such an object ever come to be in a classical universe? Numerical simulations suggest it would be fragile, fantastically fragile, collapsing at the slightest touch. And when we turned our telescopes to the sky, we found no clear evidence, no glaring anomaly that demands a white hole for explanation. Every gamma ray burst, every strange energy signature, they have a more conventional origin story, if still spectacular. This is the tension at the heart of modern science. On one side, mathematical elegance, a complete, symmetric description of gravitational geometry. On the other, the messy, empirical reality we actually inhabit. Governed by thermodynamics and quantum mechanics, the story of the white hole is the story of holding these two truths in balance. It shows that scientific progress isn't just about proving ideas right. It's often about understanding why a perfectly good, mathematically sound idea might be wrong, or more precisely, why our current universe seems to have chosen one path over its mirrored counterpart. This dynamic process defines our quest. We don't discard the white hole because it's inconvenient. We use it as a probe. It stresses our theories. It forces us to look for the deeper layer, where general relativity and quantum mechanics might finally reconcile. It pushes our observational technology to new extremes. Listening for the faintest gravitational whisper of a quantum bounce, the white hole remains a permanent question on the scientific ledger. Its persistence in the equations is a silent reminder. A reminder of the universe's hidden symmetries. Its absence in our telescopes is an equally powerful lesson. A lesson in the laws that shape our concrete reality. This is how knowledge grows, not in a straight line, but in the creative friction between the possible and the actual, between the map of mathematics and the territory of the cosmos. We started with a mathematical symmetry, a simple fact. Einstein's equations of gravity don't care which direction time flows, and from that you follow the logic. It leads you to the white hole, not a star or a planet, a region of spacetime, the perfect time-reversed mirror of a black hole. It's a prediction of our best theory of gravity, written into the geometry of the cosmos. But then you bring in the real world, the universe of thermodynamics, of increasing disorder, that relentless arrow from past to future, and that's where the elegant mathematics meets a wall. The white hole challenges that arrow. It suggests a fountain where there should be a drain, order where we expect chaos, so it exists in this limbo, a permanent question. A ghost in the machine. Its mathematical necessity is clear, its physical reality is deeply doubted, and that tension isn't a failure, it's how science works. The story of the white hole shows how knowledge advances, not by accepting easy answers, but by living in that difficult space between a beautiful idea and messy evidence. It pushes our theories to their limits. It forces us to build better telescopes, to listen for subtler gravitational whispers, to try and unite quantum mechanics with gravity. The search itself, the asking of the question that propels us forward. Even if we never find one, the white hole has already done something. It has expanded our imagination of what the universe could be. It suggests reality might be stranger, more symmetric, more interconnected than our everyday experience. The physicist John Archibald Wheeler once reflected on this. He said, "We live on an island of knowledge surrounded by a sea of ignorance. As the island grows, so does the shore of our ignorance. The white hole is a feature on that distant shore. A shape we can just make out. We don't know if it's real land or a mirage, but by charting its contours, by trying to reach it, we learn more about the ocean. We learn more about our own island, and that's the takeaway. This isn't just about cosmic fountains or reversed time. It's about the human drive to explore the unknown. To take mathematics and observation and ask, what if your journey doesn't have to end here? The night sky is full of these questions. Share that curiosity. Talk about the ideas, let them stretch your mind. If you want to explore more mysteries at the edge of understanding, consider subscribing, and tell us in the comments what concept from the edges of physics fascinates you the most. What shore would you like to explore next? Thank you for thinking about the universe with us. Keep wondering.